3, 2 then. So here we're going to talk about the graph of the tangent function. So just like before, I'm going to make my little table like we did when we introduced the sine and cosine functions. So we're going to talk about tangent and then all the transformations of the tangent function. So this is the same table that we made when we introduced sine and cosine. So I guess the first thing that I would want to do is start by generating the graph of tangent. So to do that, we'll do that kind of the same way that we did the graph for sine and cosine. So we'll go to the unit circle here. And let's think about what we remember from tangent. So remember that tangent of theta was equal to opposite over adjacent. What am I doing here? I guess it's fine. And if I multiply the top and bottom by like 1 over hypotenuse, that's okay because I'm just multiplying by 1. So I end up with opposite over hypotenuse divided by adjacent over hypotenuse. And remember, opposite over hypotenuse is sine, and adjacent over hypotenuse is cosine. So really, tangent is just going to be from the unit circle, y over x. Everybody's okay with that idea? Now, the thing I have to be careful about here is that I have a fraction. Right? I'm dividing by x here. So what values of x can get me in trouble? If you're dividing by some numbers, that's a problem. What number? What? 0. Very good. So I'm going to be particularly concerned at these two locations where x is 0, specifically at pi over 2 and 3 pi over 2. Everybody's okay with that idea? So when we divide by 0 like this, last year you saw that when that happened, when we talked about rational functions, right? We talked about rational functions last year, and occasionally they can end up with a 0 denominator. It creates a vertical asymptote, right? Do you guys remember that from last year? So the same thing's going to happen here with tangent, is that we're going to end up with a graph for tangent with vertical asymptotes. So specifically, we noted that at, hey, pi over 2 and 3 pi over 2, we had a vertical, or we had denominators that were x was 0, or a denominator that was 0. And we observe in our picture here that I've generated that we have vertical asymptotes at those two locations, at pi over 2 and 3 pi over 2. Is everybody okay with that idea? And because as we circle around the unit circle, we're going to keep on hitting these places where x is 0. We're going to have vertical asymptotes that are predictable and periodic. And is everybody okay there? Okay. So that's what my graph of tangent is going to look like. So the domain has holes in it, right? Because we have these vertical asymptotes. There's values for x where there is no value for y. There's inputs where there are no outputs. Is probably the better way of saying it. So it appears that, for example, I see an asymptote here at pi over 2, and then pi units later, at 3 pi over 2, I have another vertical asymptote, and they'll occur every pi units apart then, right? Everybody's okay with that idea? So what we'll say here for our domain is that x cannot equal pi over 2 times some number n, where n is an odd integer. So remember, integers can be positive or negative, but basically we're talking about numbers like 1, 3, 5, 7, 9, etc., or negative 1, 2, 3, or 1, 3, 5, 9, 7, 57, 89, 1,251. You get the idea. Everybody okay there? So this is just like a compact way of describing this, right? It's basically we have one at pi over 2, and then every pi units thereafter. Okay. Let's look at the range now. Notice that here we're going to have like an arrow pointing up and down at the ends of this. Why is that happening? Well, let's look for example here. As we get closer and closer to this value, the x-coordinate is getting closer and closer to 0, right? If I take a number and I divide it by something very small, the result, the quotient, is going to be big or bigger, right? If I take 1 and divide it by 0.5, I get 2. If I take 1 and I divide it by 0.25, I get 4. So as we're getting closer and closer to 0, that quotient is getting bigger and bigger and bigger, right? That's why we have the arrows at either end. So the range here is going from, or is basically all real numbers then, right? We're shooting off towards positive and negative infinity. So the notation we used there was that now let's go look at the picture here, because we're going to talk about the symmetry. I notice that this part of the graph is like kind of a reflection of that part of the graph. Do you remember what kind of symmetry that was indicative of? This was odd symmetry, when those are kind of kitty-cornered like that. Okay, so that's odd symmetry. Yes. So if I look at, I'm just kind of looking at the picture. We didn't prove anything here. But if I look at relative to the origin, notice how the first quadrant is kind of like a reflection into the third quadrant. That's what I'm looking at. Is that okay?
Yeah.
So we're just doing this a little informally. So continuity, obviously this isn't everywhere continuous because we have all these vertical asymptotes, right? You guys agree with that? But over the domain, where we've thrown out all the vertical asymptotes, we are continuous. Do you guys agree with that? So in between those vertical asymptotes, everything is connected. You guys agree? So what we're going to do is we're just going to say this is continuous over the domain. Now, remember, yes, sir. Sure. When we talked about sine and cosine, we defined what an amplitude is. Amplitude was like the distance from an extrema, a maximum or min, back to the midline. If I go and I look at my graph of tangent, do I have an extrema? No. Why not? Well, I have the arrows pointing up and down, so there is no maximum or minimum for the graph because the graph keeps on going up and it keeps on going down, right? So can we have an amplitude if there are no extreme points? No. So there is no amplitude for tangent graphs. Everybody okay there? Remember, the midline is that line that kind of divides the graph in half vertically. So here, again, shouldn't be hard to say that y equals 0 is our midline. Right? Everybody feels okay with that? This basically splits it in half. Half on top, half on bottom. Now the period, remember the period is like the shortest non-repeating segment of the graph. So if I look at the graph repeats after each vertical asymptote, right? So I do vertical asymptote, I have a section that's all new, and then it starts all over again after the next vertical asymptote, right? So the distance between those two vertical asymptotes is my period, which we had noted before was pi. So my period here is pi. Note that this is different than sine and cosine, right? Remember the fundamental periods for sine and cosine was 2 pi. So that's easy to get turned around on. And the frequency here is still 1 over the period. Okay. Now let's look at the transformation. Let's think about what that's going to be. Do that. They're not written down, are they? Feels like another site. Okay. So the domain. Can this change? If we transform the graph, can the domain change? Surely, right? So what type of transformation is going to change the domain? So what's up? So a reflection isn't going to, because the vertical asymptotes will still stay in the same place. Because if you go back and you look, we had one at pi over 2, and we also have one at negative pi over 2. So if you flip across the y, you still asymptote falls on top of asymptote, so that doesn't really change. And if we flip across the x, the asymptotes themselves are vertical, so they haven't changed locations either. Tyler?
It's kind of counter-dark, but a horizontal stretch.
Very good. So horizontal stretch is going to potentially change the locations of the asymptotes. And what else?
Shrink.
Horizontal stretch or shrink, right? So doing that will also could change the locations of those asymptotes. So those are the two things that we have to worry about. So remember that the horizontal shifts left and right are additive, and the stretches and shrinks are multiplicative. Remember that C controls the stretches and shrinks, and H controls the shifting left and right. If we go back and look at our transformation, the C is being multiplied to the x coordinate, and then the H is being added. Everybody's okay with that? Tyler?
You probably said this, but is that thing you just drew up there going to be on the test?
I can't remember if I put it on there for sure for memory, but we'll certainly answer that question before test time. I don't remember if it's in the, it's been a while since I looked at my test key or whatever, or my test version to see that it's on there. But I will for sure answer that question one way or another when we get it a little bit closer. Okay? Okay. So, how do I need to change this? Double check real quick. Okay. Let's see. So this should be oops. So this should be C times pi over 2 plus H times N. Let me just double check that real quick. So that seems right. Okay. Is the range going to change? Yeah. Sure. No, right? You stretch it vertically or whatever, it's still all real numbers. You shrink it, it's still all real numbers. You move it left to right, up and down, reflect, whatever, still all real numbers, right? Okay. Again, remember, symmetry is often not preserved with a transformation. So we're not going to worry about that. We may still have symmetry after the transformation, but times you would not. Continuity, that isn't going to change. Again, remember, you can't make any additional tears in your graph from doing one of these transformations. Still have no amplitude. The midline, will that change? Or can it change? Yes. What's going to change the midline? A shift up or down, right? If we move it up or down, the middle of the graph is changing location. Does that feel okay? And the k was what controlled up or down, so just y equals k. Can the period change? Yes. Remember, the period in this case is basically the distance between the asymptotes, the horizontal distance between the asymptotes. What's going to change that? What type of transformation? Horizontal stretch or shrink, right? What controls that? C. So this is going to become C times, or the absolute value of C times pi. Again, remember, C can be positive or negative, but the period is a distance, so it has to be a positive number. That's why the absolute value bars are there. And then the frequency is still the reciprocal of the period. So just 1 over C times pi. Okay. So to graph tangent, we need our key points. So the key points we're going to use are the following. And U and D is just short for undefined. That's where your vertical asymptotes are going to be, or where the undefined pieces are. So again, this will be important, not something I'd ask you to memorize. So let's do an example here. Let's say that we want to graph y equals tangent of 2x plus pi over 2 minus 1. So I'm going to start the same way I'd start any of these graphing problems, is I want to identify the values of a, c, h, and k. In order to do that, though, I need to make sure that my function is written in the kind of that transformation form, so I can pick out the values for a, c, h, and k easily. Is this written in that transformation form? What am I checking for, basically? Well, I need to check inside the parentheses to make sure the leading coefficient on my x is 1, which is not the case as it's currently written. Everybody's okay with that? Right, because my general form for my transformation looks like this. So we'll just start by factoring that 2 off of the x. When we factor a constant like this out, we're dividing. 2x divided by 2 is just x. And pi over 2 divided by 2 is the same as pi over 2 times 1/2. Dividing is the same as multiplying by a reciprocal. So that gives me pi over 4. And now I can easily identify my values for A, C, H, and K. Any questions so far? Okay, so I'm going to use those 4 values to write my transformation map. So Cx plus H, Ay plus K. And I'm going to perform that transformation on my 5 key points from tangent. So I'm just going to copy those down here for starters. Still doing okay? Now what I do is I'm going to take my value for x and plug into the x in my formula, and then take my value for y and plug it into the y in my formula. So negative pi over 2 times 1/2 is negative pi over 4. Negative pi over 4 minus pi over 4 is negative 2 pi over 4, or just negative 1/2 pi. And then if I take something undefined and I subtract 1 from it, that's still going to be undefined. There's nothing you can do to undefined that's going to not make it undefined. So far, so good. And then I'm just going to kind of continue working through the process here. So that's going to be negative pi over 8 minus pi over 4. So that's going to be negative 3 pi over 8 when I make my common denominator. And then negative 1 minus 1 is negative 2. 0, 0. Wait a minute. Yeah, that's 3/8. Oh, yeah, okay. Never mind. That's going to be negative pi over 4 and negative 1. And then pi over 4 times 1/2 is pi over 8, minus pi over 4 is negative pi over 8. And then 1 minus 1 is 0. And then pi over 2 times 1/2 is pi over 4, minus pi over 4 is 0. And anything undefined still stays undefined. We all okay with the things that we did there? The fraction arithmetic and everything is okay? Okay. Now what we'll do is plot our graph and then move on with our day. So I'm going to start by drawing the asymptotes in first. You know what? I'm going to just use like a highlighter. So there's negative pi over 2, and there's 0. And then in between I have negative 3/8 and negative 2, negative pi over 4 and negative 1, negative 1/8 and 0, and then I'm going to fill the space after. So every half a pi, I'm getting another asymptote. So I'll get a pi there, or an asymptote there, and there, and there, and there, and there, and same thing in the other direction. So far, so good. I find it much easier to get all the asymptotes in there first and then fill in the rest of the stuff. So I have low, midline, high, and then just kind of repeating. Sorry that I'm so sloppy. It's hard sometimes to get this to write on your tablet when it's on the kickstand. You know what I mean, guys? So it looks something like that. Victoria.
How did you, like, you didn't put periods in a full file. How did you make that happen?
Well, I just looked at the result here that I had. So I started at negative pi over 2 and went to 0. So that's my period there, is just half a pi. So I could just kind of looked at what I had. Does that feel okay? The other option could have been to just do absolute value of c times pi, and that would have given you pi over 2 for your period also. So you could have thought about it that way also. Either is fine though. It's basically doing the same thing either way. What do you guys feel about the graphing stuff? Does that feel all right? It's basically the same process that we used before, right? Where it's, you know, with what we did for sine and cosine, we're still doing the same thing. We have different key points in our graph. The finished product of our graph maybe looks a little bit different, but not that much different, right? So the other type of problem that I want to do is to take a graph and come up with the equation for tangent on it. So again, what we're looking for is our tangent equation here. So we want something in this form. basically what this kind of problem boils down to is finding the values for A, C, H, and K. Everybody's okay there? Okay. Just like we did for sine, cosine problems like this, the first thing I'm going to do is identify my midline. So looking at my picture, certainly feels like the midline is right there, right? You guys buy that? So that tells me the K value is -1. Okay, let's identify the period next. So the period, I think the easiest way to do that is look at between asymptote to asymptote. So here we're going from -π/4 to +π/4. So you went a quarter and then another quarter. 2 quarters is a half. So my period must be π/2. And I know that for tangent, that c times pi is equal to the period. So if I divide both sides by pi, or probably in this case I'd think about multiplying by 1/pi, same thing as dividing, right? Multiplying by the reciprocal. I get that the c is, or absolute value of c is 1/2. And just like the sine and cosine ones, I'd encourage you to always picture the c as being positive. Yes, of course. Victoria.
How did you get
Okay, so we started here, and I did a quarter of a pi to there, and then I did another quarter of a pi to there. A quarter plus a quarter is a half. So that's all I did, was just kind of looked at the picture and just tried to simplify it as much as I possibly could to make it as simple as I could. You know what I mean?
Yeah.
Yeah, no problem. Again, if I say something or do something and you miss it, or you're not quite sure what it is or how that worked, please stop me and ask. It's totally cool. Okay. So we have C, we have K. Let's figure out the value for A. So remember, there is no amplitude, right? But what's going to act like our amplitude in this setting is going to basically be this distance here. So you always have, on these problems, well, I'll always give you these 3 points. So basically that distance from one of the other points back to the midline is going to be your value for A. So in this case, we should be able to see that A is just 1. Or I should say absolute value of A. Going from -2 back up to -1. Jane.
So you just always look at the y?
Correct. Yeah. Yeah, the A is a vertical distance. So you're always just looking at the y coordinates. Correct. The period is a horizontal distance, so that's where you're looking at the h, or looking at the x's, I should say. Is that okay? Okay. All right, so the last thing we're going to do is we're going to find our h and then fix the sign for A. We're going to do this the same way that we kind of did for sine and cosines. Well, that's weird. Did the air conditioning just kick on or something? The heat? I guess it's probably not doing air conditioning right now. Those were on the other desk there, Becker. Thank you. So we're going to pick a point from the parent function. I will always use the point 0, 0 in these problems. In our parent function, 0, 0 is a midline point. And there can be two different kinds of midline points. It depends on what the end behaviors of that graph is doing. So in the parent function that we drew earlier, notice that here at 0, 0, the left end points down and the right end points up. Everybody can see that when we're just talking about that one piece of our graph. So that's what my notation here is describing, is that the left end points down and the right end points up. That's always the same for the parent function piece. From the transform function, I need to pick also a midline point. Well, I'm going to pick 0, -1 because I can see that lies on the midline that I identified earlier. And if I look at 0, 1, to the left of it, the graph points down, and to the right of it, the graph points up. So because these are the same type of midline points, that tells me that the A is positive. And because the x coordinate of the parent function is 0, the x coordinate for my transform function is going to be my h. And I'm done. And again, you could simplify 1 over 1/2 and just make that x if you wanted to. Okay so far? Let's do one more example, and then we'll kind of close up this section too. It was nice because here in section 2, it's very similar to things that we had already done in section 1, so it wasn't so much to worry about. Okay. So what do you guys see as our midline? Where's the midline at? Landon?
2, right?
Yeah, that's correct. So that's our midline. So K is going to be 2. Okay. Next, let's figure out our period. What's our period got to be? Well, I'm starting at 0 and going to pi. So the period is pi. And since the period is absolute value of c times pi, my c is just 1. Feel okay still? All right. Next, let's find our amplitude. Or, well, not our amplitude. There's no amplitude. Let's find our value for A. How do we do that? I'm just going to look at that distance, right? So it's 3. Everybody agree with that? Going from 2 to 5. Notice that's the absolute value of A, not just A equals 3. So we still need to figure out whether we're going to use the positive 3 or the negative 3. So from our parent function, we use the point 0, 0. which is the midline point that goes min, midline, max. And from our transform function, which point do we have to use? Has to be the one on the midline. So that's negative pi over 2. Okay. Notice that this is the left side points up and the right side points down in the transformation. Everybody see that? So what can we say about our value for A? It's negative 3. How did I know that? Those parts are opposite, right? You guys see that? Okay. And then what's our value for H? Since this is 0, the H is going to be negative pi over 2. One more. And again, you don't need the 1 over 1 there since it's just 1. And instead of writing minus a negative pi over 2, you could write that as a plus. That's fine. Any little simplifying like that, you're welcome to do. Would not mark it wrong if you did it. But since these are notes, typically when I write them in, I'm going to write it in like the least simplified down form I can so that it's easy for you to pick out kind of how those values for A, C, H, and K fell into the formula. You know what I mean? Any final questions on this tangent parts? So very much the same as what we've been doing, right? Not a whole lot different. And that's nice. Okay. So we'll stop here.